Hi guys, welcome to Deep Diver. In this video, we will discuss stack, heap, and escape analysis. We will discuss how the memory is allocated on a stack and heap, and what are the pros and cons of allocating memory on a stack and heap. We will also discuss how the Go compiler decides whether the memory has to be allocated on a stack or heap using escape analysis. Whenever we write a program and run it, memory is required to store variables, function parameter, struct, array, slices, map, whatever we use in our program, right? And the operating system provides this memory to the program, and this memory is not a contiguous memory. This memory is divided into different regions. So all this memory is provided inside the RAM only, but this is categorized into different regions. For example, we have code segment where the code lives. Then we have the data segment where if there are any global variables in the code, that will reside in this data segment. Then we have stack and heap. Okay, so in this video we will see these two in much more detail. So let us move forward and let us see this example. This is a simple program. We have a main function here which is calling func1, and this func1 is defined here, and this func1 is calling func2, which is defined here. Okay, so when this program will start executing, a stack will be provided to this program. Let us say this is the stack. So as this program will start executing and main is the entry point, what will happen here is a stack fragment corresponding to this main function will be created onto the stack. So let me mention main here. Okay, and whatever the function parameter, return values, local variable, whatever are there, that will be created on this stack. So here it is a local variable x, so this will be created on this stack frame, and then we have y. Okay, now this main function is calling here function 1, so this is our function 1. So again what will happen, one more stack fragment corresponding to this function 1 will be created onto this stack. Okay, and here again we have a function parameter called x, and then one more variable of z. Okay, so these two again will be allocated on the stack itself. Now we have a function 2 which is getting called here. So when the program execution comes to this function 2, what will happen, one more stack fragment corresponding to this function 2 will be created onto this stack, and it has only one function parameter x. Okay, so once this func2 executes this statement, return x into x, what will happen is, so this stack fragment will be popped out from this stack, and whatever the values this function 2 is returning will have the value here, or accordingly z will be updated, right? Again, when this function 1 execute this return z statement, what will happen, this function 1 will finish its execution. So this stack frame corresponding to this function 1 will also get removed from this stack, and consequently the memory allocated for the function parameter x and the local variable z here will also be deallocated, right? So once this function 1 goes out of the scope, the control comes back here, right? And when this main finishes its execution, the stack frame corresponding to this main will also goes out of a scope, and this will be deleted from here as well. Okay, so when the program finishes its execution, this entire stack will be empty. Okay, so this is how the stack is getting used. So we can say basically this is getting used for keeping track of the call chain, and also whenever it's possible it is creating variables on this stack frame as well, right? So whenever a function completes its execution, the corresponding stack frame gets popped out from the stack, and consequently the memory allocated for the local variable or the function parameters are also deallocated in the process, right? So now let us move to the next example here. So this is again a simple code. We have a function main here which is calling this foo function, which is basically initializing x to 10 and then returning its address. Okay, so let us see how it works out on the stack. So when this program will start executing, there will be a stack allocated to this program, right? So this is our entry point, this function main. So as before, a stack frame corresponding to function main will be created here, and it has the variable ptr, right? And then it calls the function foo. So when the program execution comes here, a new stack fragment corresponding to function foo will be created, which has a local variable x, right? And here it is returning the address. Okay, so let us say this x, which is the local variable of this foo, is allocated on this stack itself. Okay, and let us say the memory address allocated to this x is 0x0101. So when this foo completes its execution, what will happen again? This stack frame will be removed from here, right? And then the execution will return here again. And now here we are trying to print the value stored at the memory location this 0x001. So this ptr will be having the value 0x001. But here what happened is, when this foo finished its execution, this stack frame was removed from here, right? So once this function foo completes its execution, the memory location corresponding to this x is no longer owned by this function. It can be owned by any other, it can have any random values like 10, 20, 100, whatever, or maybe some garbage value, as well as the same memory address can be used by some other function, right? As this is not currently owned by the function foo. So this pointer here, this pointer variable, is basically referring to a memory location that is no longer valid. So it is invalid, right? So this can be a problematic scenario, right? Because here in this line fmt.println star ptr, here ptr is pointing to a memory location that is no longer valid. So this can be problematic. This is where Go compiler comes into the picture and decide, since this variable x can be used by some other piece of code in future, let us not allocate this variable x on the stack, but instead use heap. Okay, let me delete this stack. So let us say stack was up to here. So this variable x will not be allocated on the stack but on the heap. Okay, so here we'll have the memory address reserved for x. Okay, so what will happen now, once this memory is allocated on the heap, even if this function completes execution, this x will still survive. So when this ptr will try to address the value at x, it will still point to a valid address, right? So this x will have value 10 here, and this ptr will definitely print only 10. So to summarize, what is the effect of allocating memory in the heap? Even if this foo function completes its execution, the memory address corresponding to the x is still valid, and later if any piece of code which wants to access the memory corresponding to this x, they can still access it, right? Now let us move further and see one more example. So this is a similar kind of example. So here we have a user struct, and then we have a create user which is returning pointer user. Okay, and then we have a function main which is calling this create user function here. Okay, so here again what will happen, when this program will start executing, a stack will be allocated to this program, right? First, a stack fragment for main will be created. It will allocate the user variable on this stack fragment itself, and when this create user gets called, Go compiler will come into picture and it will check that it is again returning a address of this user variable, right? So this will decide this u can still be accessed by some other code in the future. So again, it will not create this u variable on the stack fragment corresponding to create user, but it will move this u to the heap. Okay, so u will be allocated on the heap. Okay, so once this finishes its execution, this stack frame will be popped out from this stack, but as this u is now allocated on the heap, it is still valid. So when this line will execute fmt.println user.name, it will print whatever the value was given here. Here it was Ravi, so it will print Ravi. Now the question arises, when we were using the stack here, and whenever a function was completing its execution, the corresponding stack frame was getting destroyed, and consequently the corresponding variables were also getting deallocated. But here in this case, as the heap survives the function scope, when this memory will get freed, and who will be responsible for that? So that's where garbage collector comes into the picture. So it is the responsibility of the garbage collector to clean the memory, and this garbage collector is handled by the go runtime. So when does this garbage collector will free this memory here? So if we see the code again, in the next line we are doing user is equal to nil. So a block of memory will be cleaned up by the garbage collector if that block of memory cannot be further referenced by anything. So here, once we assign this nil value to this user variable, we have lost the address of this u created in the heap. Okay, so after this line, this memory will be marked for deletion. Marked for deletion. So whenever the garbage collector runs next time, it will clean this memory. Okay. Now let us look into what is the difference between stack and heap. So this is stack, this is heap, and these are the various features. Allocation speed on stack is very fast as compared to heap. Okay. And deallocation is automatic. Whenever the function goes out of stack, the corresponding stack frame gets removed from the stack. That's why the deallocation is automatic. But we have seen in case of heap, we need garbage collector, right? And the size of a stack is smaller, but a heap is much larger than the stack. Okay, so if we have a very big object, then that object will be created on the heap instead of the stack. Okay, and the lifetime of a variable created on the stack is, like as we have seen, this is a function scope, but for the heap it is arbitrary. Okay, it will not be removed from the heap till we have a reference to that memory, right? And the access speed, the stack is faster, heap is slightly slower. Okay, and this stack is managed by this runtime stack, and this heap is managed by garbage collector, as we have seen. Now let us move into the escape analysis. So escape analysis is a compile time analysis that determines, can this variable be safely remain on the stack, or does it need to escape to the heap? Okay, so all those examples we have seen, this one, this one, and even this one, all can be considered as example of escape analysis, right? So while doing escape analysis, compiler basically asks, will somebody use this variable after this function returns? If that variable can be used in future, then that variable is allocated on the heap, otherwise it is allocated on the stack. So this is what we have discussed in the previous example. We have asked this question already, right? And then decided whether the memory has to be created on the stack or the heap, right? So let us revisit similar kind of examples again. Okay, we have already discussed this example, but here we are just doing it more formally under the heading of this escape analysis. So this is the first example. Here we have a function foo which is just returning an integer value. Okay, so here we have a variable x and we are returning the variable x here. So who does the escape analysis? Go compiler, right? So the Go compiler will come here and it will check that this function foo is just returning a value. Okay, and once this function returns the value here, which will be 10, there will is no point any other piece of code will try to access this variable x, right? So this x will be allocated on the stack. Okay, now let's move to the second example. So here the function name is again foo, but here it is returning an integer pointer. Okay, as we have seen earlier, Go compiler will come into the picture and it will check. Okay, here this function is returning an address. So any function which will call this foo may try to access this address, right? So this variable outlives its function scope. So this x will be created on the heap but not on the stack, right? So let us move to the next example. This is the similar to the example we have seen previously. Here we have a user struct and we have a function new user here, right? And again it is returning address of you. So here Go compiler will again check that this new user is returning a pointer, and whoever will be calling this new user function may try to access this address. Okay, so this variable must outlive its function scope. Okay, so this will be again will be created on the heap. Okay, now let us go to the VS Code and I will show you the evidence of escape analysis by the Go compiler. So this is our VS Code and I have already created a folder named 14 underscore escape analysis, and I have this file here escapeanalysis.go. I have already copy pasted the code we have seen in the iPad. Okay, so we will try to execute this code one by one. Okay, so let me uncomment first this user struct one. Okay, and here we will call the function new user. Now let me open the terminal. Now to show you the compiler uses escape analysis, I will use the command go build minus gc flags is equal to minus m. Okay, and then we will need to give the file name. So this minus gc flags is equal to minus m basically shows you the optimization done by the compiler while compiling this code. Okay, so if I run this code, you can see on the last line, right, moved to heap. This is corresponding to line number 18. So on line number 18 we have this statement, and it is getting printed here that this u is moving to heap. Okay, now let us go to the other example. I will comment this one and uncomment this function foo, which is returning an integer pointer, and here instead of new user we'll call foo. So if I run this code again, you will see on line number 9 it is x colon equal 10 and it is telling here moved to heap. Okay, now let us do the same thing for the other function foo as well. So this is the function foo which is just returning an integer value. Okay, so if I run the code again, you will see there is no such thing as moved to heap got printed in this case. Why? Because this time this x does not escape to the heap, but it was allocated the memory on the stack itself. So that's it for this video. See you in the next one.